Okay, well, this is our next course of the day. We are going to hear Gaston Garcia. I don't remember the title of the lecture. Gaston.
Yeah, thank you, Gisela. Thank you, everyone, for being here. And as Gisela said, I'm Gaston Garcia from the La Plata. And we're going to talk about this. This course is going to be about representation of compact groups. So in this first lecture, I'm going to introduce the basic definitions and some examples and some key facts that will help us to understand representation of compact groups. And in the view of that, we can extend all these notions to more non-commutative settings, in the sense that we are going to work with algebraic functions that are going to be non-commutative. And the idea is to understand quantum groups coming from this kind of thing. So this is the goal, but here I'm going to talk only about classical things. So this would be more or less the background for the next course of Christian Freud, I hope, okay? So let's start with very basic definitions of what is a topological group. So everyone knows that a group is a set with two operations. One is the multiplication and the other one is the inverse. And the group has a unity or a unit. And if one talks about abstract group, that's it. Okay, the multiplication, this map called the multiplication has to be associative, and the inverse has to satisfy the axioms of an inverse. But if we're talking about the topological group, the first things that we need is that the set is a topological set. So set is endowed with a topology. Any topology, okay? And we're going to see some examples about that. And since every time we talk about things with some property, we want that the structural maps, respect that structure. So the multiplication and the inverse here has to be continuous map. It means that it respects the topology, okay? So the continuous map means that the pre-image, so if someone forgot what is a continuous map, I can tell you. So any question that you have, you may interrupt me and ask me, okay? I'm trying to be as basic as possible in the first lecture, okay? So a continuous map, a map between two topological spaces, say G and H, is continuous if the pre-image of any open set is open. Okay? So when we talk about compact groups, the idea is that we are supposing that G is indeed a compact group, a compact set, in the meaning that it's compact and Hausdorff, okay, with respect to the topology. So the first trivial examples are given by the finite groups. So finite groups are compact groups with which topology? So we have to define the topology. So we fix the discrete topology, which means that the points are the open subsets. Or open, of course, they are also closed. I cannot write, so sorry. I have a lot of jet lag. Closed sets. Okay, since the set is finite, because we are talking about finite groups, it is compact, okay? So any finite group is compact. So as everything is clear, because we are working with the discrete topology, the product and the inverse are continuous maps, okay? So we can leave this as an example. So you start by playing with this very easy example. So both product and inverse are continuous maps. So in the whole course is going to be about compact groups. So finite groups are the first easy example of compact groups. So anything that I'm going to talk about, theorems and properties and things like that, also hold for finite groups by looking at the discrete topology. So in some sense, this short course includes the theory of finite group, the representation of finite groups. The theorems in that case are easier to write because everything is discrete, okay? The thing in compact group is very interesting because we have a lot of very, very nice examples. So the first easy group that we have is the circle group, the unit circle group. And it has a lot of descriptions. So because we can play with the topology and things like that, so the same groups appears in different ways that one can describe. The first one is, okay, the circle group is just if you look at it as complex numbers, it's just the complex numbers of module 1. So if I describe this set like this, I will write this like U1. So U1 is the set of complex numbers such that they have module 1. Yes, and this is something like this. If you write in binomial form, yeah, and if A and B are real numbers, so this is isomorphic. Instead of writing as complex numbers, we write them as matrices, and we put them as matrices like this. And with this description, with A and B real numbers, they satisfy that the determinant is 1, and this is our rotation matrices of determinants 1, so this is SO2, the special orthogonal group of 2 by 2 matrices over R. So this is one can prove that this is actually an isomorphism of groups, of topological groups. Yes, this is also an exercise. So we have the same description for this group. And yes, why this is a compact group? So if we look at as the set of complex numbers of model 1, we can take the topology in C. The topology in C is actually the topology in R2, and in a lot of examples that I'm going to see here, we are considering topology of Cn or Rn, R2n, and in R2n, a compact set is a compact Hausdorff set is a set which is closed and bounded. Okay. So let me write this. A subset of, say, Cn, here n is 1, okay, is compact on Hausdorff if and only if it is closed and bounded. So this is, in this example, it's clear that this is closed in R2n, okay? So it is clear that a U1 is closed and bounded, okay? The bound is exactly what is given by the very definition. And of course, we can see this example as the image of a map from the real numbers to U1. So we take any real number T and we send it to a complex number to PIT. Of course, it has a kernel, this one. Yes. So we're looking at let me see if I can do that. No, let me do it again. No. Okay, be patient. So this is the unit circle, it should be the unit circle. So this is U1, and this map has a kernel, and this kernel is given by the multiples, the integers. So actually, these two groups are isomorphic, R over Z and U1. Okay, so this is another way of looking at U1 as the image of isomorphic of R over Z. And if we look at this image, and this one is supposed to be a circle, it's not a circle for me, it's very bad. So for example, the inverse map, the inverse of any set, in this case, is the conjugated number. So if we take here this set here, the inverse is given by Z minus 1, which is the conjugate, which is the symmetric point with respect to the x-axis. And if we take any interval open set with containing our Z minus 1, the image is exactly an open interval here. Okay, so you see that by drawing, it is a continuous map, the inverse. Yeah. So this is more or less how to prove that the inverse is continuous. In this case, if we're looking only at this topology. Yeah. And in the next examples, I'm going to say how do we prove that everything is continuous. Yeah. Actually, we're going to talk about what is called matrix groups. So the next examples are going to be about matrix groups, and for matrix groups, it's a very easy way to prove that they are compact groups or continuous, at least continuous. The product and the inverse is given by continuous maps. So again, everything is full of exercises. So exercise, prove that the product and the inverse are continuous maps. So the next example, the next more complicated example is U2 is not the group of music U2. I don't think they know a lot about compact things. It is the unitary group of 2x2 matrices, but actually I'm going to write, I don't know what I did this. We can write this in general as UN. So we can take, of course, n equals to 2, and then we have it. So what is UN? So above I described U1 as the complex numbers of modulus 1. So UN is going to be the matrices, invertible matrices of n by n with complex coefficients, such that they are unitary. So the adjoint matrix times A is the identity. So the adjoint matrix is the inverse. So this is called the unitary group of n by n matrices. So of course, U1 is exactly U1. Okay, so here A star is equal to A conjugated and transposed. So what is the topology here for this group? So this group is a subgroup of GLNC. okay? The G and L and C are the matrices of n by n, which are invertible. And which is the topology there? So we consider the topology of this GL and C as the topology in the induced topology as a subset of say first a C n by n or C n square. So this is the product topology, and this is inside of R2n squared. So to see if something is continuous, in this case, is quite easy because we look at the coordinates. So if the multiplication is given by functions, by in each coordinate is given by functions that are continuous, then we will see that the product is continuous. Or the same with the inverse. And for matrices is great because we know that the formula of the multiplication of matrices is very easy. But it's not easy if you are a first-year student, it's quite complicated. But we know that there are polynomial functions on the entries of the matrix. So it's more continuous than that, it's difficult to find, okay? So I'm going to write this. So let me choose a color and I'm going to write this down what I said. So the multiplication in UN is the one induced from a set of matrices. And this one is given by polynomials on the entries of the matrices. So it is continuous. So every time we have a matrix group like this, we're going to see the matrix groups inside the group of invertible matrices, and the multiplication is going to be directly a continuous map. So what about the inverse? So for the inverse, we have a beautiful formula how to invert a matrix. So we know, it depends now on how do you denote this, or how you learn this, that the inverse of a matrix is the inverse given by the inverse of the determinant times the adjoint matrix, which is the transpose matrix given by the cofactors. Okay, and I'm not going to write this down because it's more complicated than it sounds, but it's easy, and everyone knows how to compute the inverse like this. Actually, nobody does it like this, I think. But what is the thing here is the inverse of a matrix is given by a rational function in each entry. So the functions given the inverse in each entry is given by a rational functions on the entries of the matrix. Why rational? Because we have the determinant here. And the determinant of a matrix is given by a polynomial function. And the adjoint matrix is computed by the cofactors. Each cofactor is a determinant. The determinant is again a polynomial function on the entries. So in every entry, we have a rational function, and these rational functions are continuous because we are dividing by something that is not zero, because we are looking at invertible matrices, okay? So I'm going to write this down, what I said. So this implies that the entries of A minus 1 are given by rational functions that are continuous. So perfect. So every time we talk about a matrix group, we know the structural maps are given by continuous or rational functions, which are by polynomials or rational functions that are continuous. So we're okay with that. So we're fine with the topology. Well, now what about to being compact? So actually, the unitary metrics are in a bounded set. In the first example of U1, we saw that they are actually the circle of radius 1. And in more dimensions, actually, they're all the same. Yes? And how do we see that it is bounded? Because the columns of every unitary matrix form an orthonormal basis. So, yeah? But they are given by vectors which has norm 1. Yeah. So UN is compact since every column of a unitary matrix I don't know how to say it. So the columns, since the column of any unitary matrix form orthonormal basis of Cn. Yes, so the columns has norm 1. So if we look at the entries, they are all inside the big ball of some radius, 2n, I think. Yeah, we can, you can write down the details, but this is every matrix is inside a big ball of some radius. Yeah, well, you have to do the calculations and find some radius. Yeah, so it is bounded, and one can prove that it's also a closed set. Yes, it's given actually what we saw. Well, we say it is a closed condition. This one. So, okay, these are our very nice compact groups, the unitary group of matrices. So we're going to look at the representations of this unitary group, okay? This is going to be our toy examples. Not like toy, but yeah, the irreducible representations are very beautiful. So inside, this is another group. Inside the unitary group of n by n matrices, of 2 by 2 matrices, we have the special unitary group. So the special unitary group is given by the matrices, which are unitary, and such that the determinant is 1. So this is the special unitary group of 2 by 2 matrices. Well, it turns out that this unitary group is isomorphic to SO3 of R. So the special orthogonal group of 3 by 3 matrices given by the rotation of in R3. Yes, in the last lecture, we're going to talk about a lot of representations of these groups. So maybe I'm still thinking about this, if I'm going to show you why this isomorphism is true or not. This isomorphism is used a lot by the physicists. Okay, they love this isomorphism. In physics, actually, it appears a lot. The unitary group and the orthogonal groups acting and everything. So the representations of these are very important in physics. Yeah. So as I told you, we are going to talk about matrix groups. So there are closed groups or compact subgroups of the invertible matrix in R or in C, okay? In R, actually, when we talk about R, we are looking at the orthogonal groups in general, and GLN for the unitary. Of course, we have a lot of compact groups in nature, yes, but to stay focused in this course, we're going to talk a lot about unitary and orthogonal groups, okay? All right, so are there any questions so far about the examples and definitions?
I
Uh,
I have a question. The field can only be R or C.
in this course, yes,
All right.
because we're going to talk about topology. One can do that and for finite fields also, and things like that. Yes, we can do that. U2 is a double cover, but if you put an S with the special, that's you get only one cover. Yes, because they are not connected, things like that. Mm. You see what in the calculations that we get the one cover. Yes. Okay. Yes, I'm not. Yeah, there are a lot of beautiful things about topological groups that I'm not going to talk about because of the time. Yeah, we don't have enough time. But the properties of connectedness of groups is also very important and very nice. I have a lot of properties doing the coverings from one group to another, and the componented identity and things like that. So for example, you can look at the book of Knapp about Lie groups and things like that. It's a very nice introduction about compact groups. Yeah. Actually, there's a lot of bibliography references about compact groups or topological groups, and more about Lie groups, which are more than topological groups. They have a differential structure. Okay. So now, so every time I want to talk about a compact group, we can think about the unitary groups or the orthogonal, the special orthogonal or the orthogonal. Okay. So now we take a group, a compact group, and we think about the functions of them. This is an idea, it's an old idea of mathematics that has to do with when I think this due to Grothendieck, but I'm not sure because it's very old, so maybe it's not quite precise, this reference. Also, Gelfand do that a lot. Instead of studying a group by its structures and the properties, we study the functions on them. And which functions? Since we are talking about topological groups, now we're going to talk about continuous functions on them. Yes? So continuous functions on them are functions from the group to the field that, again, is going to be C or R. Yeah? Because we can do it in more general fields, but in this course, we're going to talk only about C or R. There is a very nice, sorry, I talk a lot. There is a very nice theory of groups in p-adics. We're using the p-adics field. It's very beautiful, but it's too complicated, okay? Now, we're going to be basics just to understand what we're talking about representation of something, okay? So we are going to fix for now this C or R. Actually, I'm going to write C everywhere, okay? So given a continuous function, one can define what is the translation of the function on the right and on the left by any element of the group. And why we can do that? Because in the group we have the inverse and the multiplication. So we define the function. So we pick a function. We pick a function f, a continuous function and an element of g, and we define the function by multiplying on the left by this function by an element of G is the function. I'll define the function by saying which is the result on an element of G is given by f of, say, wait a second, because yes, it is by the multiplication of x minus 1 times y. And this defines another continuous function, because why? Because we know that the multiplication is continuous and the inverse is continuous. And f is continuous, so we are okay. Yeah, so this is the left translate of the function. I put it the other way around, right and left translation, and I wrote first the left and then the right. Okay, I will have to correct it. And the right translation is the multiplication of x on the right is given by the multiplication on the right. Yeah, so we can translate the functions and by doing this with a fixed element of x. So why is this important? Because we need functions, we need something that is invariant under translation. What is the things that we need? The whole theory is based on the fact that we have something that is a measure in a compact group. This is a very deep result for compact groups. And I'm not going to give you the proof of that because this will demand the whole course in proving that any compact group has a measure. But I'm going to use that because I want to talk about representation of groups, okay? Not the group or the course on compact groups. So this measure is called the Haar measure or the Haar integral. Yeah, it has different names of the same thing. So what is this Haar measure? So given a compact group, one can prove that there exists a unique linear map from the set of continuous functions to the complex numbers, such that it has the following properties that makes this unique, okay? It is a unique map. Yes, unique. First of all, it is positive. What does it mean? If we take a function that is bigger or equal than 0, when I said bigger or equal than 0 means it's bigger or equal than 0 as the values are taken in R, okay? Because we are using the order in R, not in the complex numbers, okay? The measure is bigger or equal than 0. The measure of the function 1, I didn't say who is the function 1, but the function 1 is the constant function, okay? The function 1 is the constant function given by any element of x gives you 1, okay? It's constant, so it is continuous. So the measure of 1 is 1, and this measure doesn't see the translate of the function. So if we translate the function on the left by any element of the group, then the measure is the same. So it is actually what one thinks about the measure. It doesn't depend on translations. So we say that in this case, M is left invariant. And by construction, one can prove that it is also right invariant. Yeah. So there exists this measure for different groups. It has different forms, okay? We're going to see 2 examples on who is the Haar measure on these groups. So since this is a measure, we write something like integral thing. So the measure of any function f, we write something like this, like the integral of f over g. Yeah, I'm going to write more this notation than the one in the middle. So the function is the measure is defined on the functions. So what is the measure on a subset of the compact group? It's just the measure applied to the characteristic function on the group, okay? So the first consequence that we have about the measure is left invariant. So if it is left invariant, so we know that the measure of any point is the same as the measure of the identity, okay? Yeah, because it's left invariant. So every point has the same measure. And okay, if every point has the same measure, we have the first consequence is because so we also assume that I assume that the measure of 1 is 1. So in our notation is I have a lot of ways of seeing that, but it is the function, this function on G, and this is actually also the measure of G because it is the characteristic function on G. So the measure of G is 1. So this implies that the measure of any point is positive. This implies that G is finite. Yeah, because the measure, yeah. If not, the measure of any point has to be 0. And in that case, the measure of any point, so the measure of E, is equal to 1 over the order of G. Yes, with the measure of all the points is the sum of its measure. The measure of G is the sum of the measure of all the points. They have the same measure, so the measure of any one has to be 1 over the order of G. Yeah. So again, so we know in a finite group, so if we have a finite group, the measure of any point is the same, and it is this one for any x in G. And what is the measure of any function? The measure of any function is given by the integral, but actually the integral transforms now into a finite sum because we have the discrete topology, yeah? So it's defined over the elements on G of f evaluating x. Yes? So here, the continuous function on G, since we have the discrete topology, so these are the functions of G and C such that f is just a function because we have the discrete topology. And the algebraic notation of that, you can find that this is C to the G, or this is the algebraic notation. So if you find a book of of representation of finite groups, you will find this notation. Or in algebraic geometry, they will call it O of G. So this is the hard measure of a finite group. And now, what is the measure of our circle group? Okay. The measure of our circle group is given by the following. So we take an f, a continuous function on the circle group. It is called T because T is a torus. So in geometry, one calls the circle groups a torus. So this is why it's called T. Yeah. It has a lot of names, the same group. I don't know. I'm following some books, so I will call it T. But when I say U1, SU2, it's the same group. Yeah. So the measure of F is given by the absolute value in this case of the integral over the circle of the function f z over z. Yes, the integral, the complex integral. Yeah, and this is an exercise. The idea is not to follow the proof of the existence of the half measure. The idea is we take this measure and one proof that it satisfies all these properties. Yes, if it satisfies all these properties, it has to be the hard measure because there is only one hard measure. Yes. So if you find a formula that satisfies these properties, the A, B, C, and D, A, B, C actually, D, it follows from the other one. If one proves that thing, then it is the hard measure. Okay, so we have a hard measure in this case. Okay, so far so good. Now we set our basic definition of what a compact group is, what are the easiest examples, and every compact group has a hard measure. Okay, now we're going to enter into the field of representations. What is a representation and what do we mean by a representation? So the first thing that we need is we're going to try to see any group as a subgroup of matrices. And this is given by the idea of representation. So maybe we are talking about an abstract group, but we don't like a lot abstract groups. What do we want? We want to see them as matrices because we know how to do a lot of things with matrices. So to see a group as matrices, we need something that relates our group with something with matrices. And this is actually what is a representation. To have matrices, we fix first a finite dimensional vector space. And to put everything together, we think as in the old times, in the 18th, 19th century, that any group is a group of transformations of something. If we think a group as a group of transformations of a finite dimensional vector space, then everything in the group, every element, is going to be a matrix acting on this vector space. So we're going to see the elements as matrices acting on this vector space. So this is why we are going to talk first about finite dimensional complex vector spaces, because we're going to see every element of the group as something transforming the vector space. So the first thing is, what is a transformation of this vector space? Is just an invertible matrix, okay? So first we define GLV. What is GLV for any vector space? For any finite dimensional vector space, it's just the space of invertible linear transformation. So clearly it is a group by composition. Okay, and the inverse by the composition again, and because they are invertible linear maps, where we have the inverse. So, for example, if we take V to be this vector space C to the n, then actually any finite dimensional vector space like this, G of V is actually isomorphic to the group of invertible matrices over C. Yeah. Okay, so what is, given a compact group, what is a finite dimensional representation of the group? It is given by a pair. A pair, what does it mean, a pair? Actually, in the future, we're not going to talk about any pair. We're going to talk about the map or the space. The pair, we have to say the vector space where we're acting and the map that gives us the action. So if the vector space is very clear from the context, we're going to forget that. Or if the action is very clear from the context, we're going to forget that. So it depends on the example, yes? But actually, we need the two things to talk about representation. We need a finite dimensional vector space and the formula that gives us which is the way that the group is acting on the vector space. So this is translated into saying that we have a group homomorphism from our group G to GLD. Yes? This is an abstract representation, but here we are talking about compact groups. Compacts are topological groups, so we need that this map should be nice enough. So being nice enough means it is continuous, okay? So in conclusion, a finite dimensional representation of our compact group is a pair given by a finite dimensional vector space and a group homomorphism between G and GLD, which is continuous. Yeah. A way to see that this map is continuous, another way, which is equivalent, is saying that this map that goes from G times V to V, this one, is continuous in both variables. We're talking about finite dimensional vector spaces, and every finite dimensional vector space is isomorphic or homomorphic to C to the n, and C to the n is the topology that we were discussing above, okay? R to the n. So to see that something is continuous, again, we fix, for example, a basis, and we look at each coordinate. If the map given in each coordinate is continuous on the entries, then it is continuous, okay? So it's not so difficult to see every time we have an example if something is continuous or not, in general, okay? If not, sometimes it may be hard. So when we have a representation, a finite dimensional representation of a group, the vector space is called the representation space. And the dimension of the representation is just the dimension of the vector space. Yes? Now, we know that if we fix a basis of this vector space, then we get from any element of the group acting on the vector space, we can get a matrix, okay? So how do we get the matrix if we have a representation? So let's pick a basis of our vector space, yeah? So we pick an element of the basis. So let's pick up, so take J between 1 and N. So let's take Bj. So if we take Bj and we act by an element in G, then this element is clearly a linear combination of the elements of the basis, okay? And these elements here are the coefficients of our transformation. So what we learn in our first course is linear algebra is that the matrix of our linear map, the linear map given by the image of pi on X, in the basis B is given by this matrix, okay, Aij. Yeah? So if we pick a dual basis of this basis, so we know that the coefficients are written like this. So every Iij is just the dual function, or Fi applied in the transformation of Bj. Yeah, this is the formula for our coefficients in the matrix. So you see here that we can describe the action of any element X by a matrix. The matrix given by these coefficients. And the matrix given by these coefficients is given by this formula. Yeah. So if we understand this formula for any X when we fix a matrix, then we understand the representation. Yeah. So since we know this, if we have a nice formula for these things, we put a name for that. And the name for that is, we call these things matrix coefficients. And this is going to be very important for the course of Christian, if we want to understand something. So given a representation, we fix a basis, and we take a matrix of this basis, and for any ij, so for any I given as the row and j the column, we pick the coefficients of the formula, and this gives us a function from G to C, and this one is called the matrix coefficients. Of course, with respect to a basis B. Yes, we fix the basis. So every time we fix a basis, we have a matrix coefficient. We change the basis, we have another ones. Yeah. Okay. In the case we want to talk about infinite dimensional representations, so the group is acting on an infinite dimensional thing. We will need a lot of things, so we're not to talk about infinite dimensional vector spaces, but infinite dimensional Hilbert space. Because why? Because we want to have an inner product. Okay. You will see that in the next lecture why we need an inner product. It makes the things easier. And what turns out is that eventually, so one proved that any representation, finite dimensional or infinite dimensional representation, is a direct sum of unitary finite dimensional representations. So that's in the Bernoulli theorem. And the thing is, okay, if this is true, we only need to understand what are the unitary finite dimensional representations. And this is what we're going to do now, next. The first thing is, okay, you didn't talk about unitary things. And it was about, I think, maybe I don't have the time, but there was the idea to talk it today. If not, in the next class, I'm going to talk about unitary. But the key fact is that any finite dimensional representation is actually unitary. We can find a way to prove that it's unitary. So when describing unitary finite dimensional representation, we are going to talk about the blocks. If we understand these blocks, we understand the whole representation. Yes. And as I said before, if we want to prove the continuity of the representation of the map given the representations, we just look at the matrix coefficients of the representations. And for any ij, we look at these maps. Yes. And the thing is that this map takes values on C or R, depending on the example. And we see directly from the formula that these things are continuous or not. In general, if we'll use, for example, matrix multiplication, then we will see that immediately that these things are continuous. Yeah. So from now on, from this lecture and what is coming next, every time when I talk about a group, it's going to be a compact group. Okay. And when I say representation, it's going to be a finite dimensional representation. And by default, I will work over the complex numbers. But if I talk, for example, about a representation of the special orthogonal group, it's going to be about the reals, okay? So first example, easy example. So as I told you, the very, very easy examples are the finite groups. This is okay, when I say easy, they are not easy, but in this case, it is easy in terms of the topology, okay? The theory of representation of finite group is not so easy. It's very rich. But in terms of topology, is we have a problem, a less problem. No, we don't have that problem of thinking about continuity. So in finite groups, a finite dimensional representation is just a group homomorphism. As I said, we don't care about the topology here because we are thinking about it as discrete topology. That goes from G to GLV. Again, V is a finite dimensional vector space. Yeah, so for example, so let's take a very easy example. So you get some example for today. Take Cn, the integer numbers modulo n for some n. Yeah, you pick the n that you want, your favorite n. So you take a complex number, which is an nth root of unity. And we take pi to be the map given for set n to C star. C star are the invertible linear maps from C to C. So here we are considering V just as the complex numbers. So it's very, very easy vector space, the one-dimensional vector space. And the representation is given by, we take any integer modulo n, let's put not I, let's put k, and we send it to omega to the k. And this gives us a representation. So it is one-dimensional. So in this case, we are looking at the elements of the group, the cyclic group of order n, as numbers, okay? Which numbers, roots of unity, that are actually inside the circle group, okay? But they are finite. So in this case, it is enough to understand these representations to understand the whole group. So the idea is we look at representations that are actually easy to describe to understand the whole structure of the group. In this case, if we understand these representations, we understand any representation of the group. Yes. Of course, if you take the nth root of unity equal to 1, because 1 is a root of unity, then we get the trivial representation that sends any element of the group to 1. With that representation, we understand nothing. We need other things. So how do we understand the group? By taking different root of unity. So this is for a finite group. For a matrix group that we were talking before, we take what is called the standard representation. So for the standard representation, so we take the vector space to be C to the n or R to the n if we are talking about the group, as I told you before, SONR. And the standard representation is given just by matrix multiplication. So we take the pi to be, that goes to the group, to GLM Cn, which is actually isomorphic to the invertible matrix or n, and to any element of the group, to any element A of the group. We're talking about matrix groups, okay? We send it to the map given by P of A of any element X is just A of X for any X in Cn. So it's given by matrix multiplication. of one column, okay? Cn is one the column, by the column multiplication. So x, we see x as a column. So by the formula, all the formulas are polynomials on the entries, so this is very, very continuous. And why? The last things I'm going to do is let me check that this one is a group map. So pi is a group map. So pi is continuous because what I said before. So let us see that pi is a group homomorphism. So I do something today. So the first thing is the pi of the identity matrix in any element is just the identity matrix times x, which is x. So this means, we are working for any x in Cn. So it means that the image of the identity is exactly the identity map. So the pi of 1 is 1, and if we take two matrices and we apply it to a vector, it is the product of the matrices applied to the vector, which is, by what we know about multiplication of matrices, is associative, and this thing is pi of A acting on the vector B times X, which is pi of A of pi of B acting on X, and this is pi of A composed with pi of B acting on X. So I'm writing composing because I want to stress that the product of the group goes to the composition of the linear maps, okay? This is actually what we want. And this is true for any A and B in our matrix group. So these are the very basics of representation of compact groups. So I give you some examples. And the next lecture, we have to keep these examples in mind because we're going to talk about a lot of structure, yes, a lot of properties about representations. How do we get more representations from the ones that we have? And deep results that how to describe all representation by using the more simple one that are called irreducible representations, okay? And Schur lemma and things like that, that is very deep in the theory. So this is all for today. And are there any questions of what we saw today?
So I have two actually. First one, when you talk about at the beginning of the presentation, when you talk about the hard measure for a group, and you said that if the measure of an element is bigger than 0, then the group must be finite.
Yes.
I don't see it clearly.
Because it has to be.
How do you prove that? Or is it a difficult?
No. It's not difficult.
All right.
Because it is a measure, okay? So so you see that G is the union of the points. Yeah.
All right.
And you know that the measure has to be 1.
Okay, then you have
This is a disjoint union, yes. So
okay.
if
Then you
yeah,
have a sum and you
Yes.
can use that
Yes.
if it's infinite. Okay, okay,
Yes, it has to be the sum of the measure of the things. Yeah,
okay.
so it
Perfect.
forces to be finite, and if they're all the same measure, then you know that they have to be this
Yes,
measure.
of course. Okay, all right. And
Yeah.
one thing, hard measure is a generalization of Lebesgue measure, or it isn't?
It isn't.
Because the construction, or at least its properties, are quite similar to Lebesgue
Yes,
measure.
because it's the properties and the things are we are using forms on a set. So actually, we are using the Riemann integral on the set.
Okay,
So
all right.
since we are using Riemann, it has the properties of the Riemann, which has the properties of Lebesgue. Yeah. But yes, in general terms, one proves the existence using the Lebesgue integral.
Okay,
Yeah,
so
because you prove
it's
it for sigma
okay.
and delta sets, and you construct them
Okay,
like that. Yes, we use the Lebesgue integral. But things we are working on matrix things and the complex numbers and real numbers, actually we are going to use the Riemann one, right? And forms. This is what you use in general.
okay. Thank you.
Welcome. Are there any other questions or comments or whatever you like to say?
Okay, if not, I will stop the recording.
We can stop the recording before
Yes.
that.